First, I'll give a quick introduction about ICN, and then and also the motivation behind our work, and then I will go through the system model and static game and the dynamic game that we have designed to evaluate this problem. Then at the end, I will show some numerical results and talk about the future directions. First, why ICN? Recently, vast majority of internet interaction relate to content access such YouTube, BitTorrent, or Netflix. But the thing that is important for the user is just the information, not the location that the content is, or even perhaps not how the content delivered. Then we need to have a new approach to support this paradigm, and here ICN comes to mind. Actually, ICN is a new communication paradigm to increase the efficiency of content delivery and content availability in the network. And the most important thing about that is all the network infrastructure should actively contribute to content caching and distributing the data. For example, if I have this model that is consists of one content provider or content distributor, two transit networks C1 and C2, and three access network A1 to A3, and also some users here that can switch from one access ICN to another, all of them should contribute to caching and distributing the data. For example, if one user under the access ICN A3 asks for some content, and for example, A3 doesn't have this content, A1 should be able to somehow distribute its content to the A3, and then A3 deliver it to the users. Now with the example, I will show you how the user can get the content. Assume that some of these users just send a request to the access ICN A1 for a piece of content that can be that movie that we have shown above. And the first thing that access ICN need to think about is, do I have this content or not? If it has, everything is okay, then it will deliver the content to the users. But if the answer is no, then it needs to fetch this content from somewhere else. And it will start to send requests for transit ICN C1 or C2. And if one of them has this content, then it will deliver back to the access ICN. But it doesn't have, then it will, the transit ICN also send a request to the content distributor, and for sure content distributor has this content, and then it will deliver the content to the transit ICN and then access ICN 1, and at the end it will deliver it to the users. But after this process happening for some time, and all of these users request for the same piece of content, then access ICN needs to decide, should I cache this content or not? And this is the main thing in ICN. All the network elements need to cache the popular content and then distribute this kind of content. But actually, the motivation behind our work is, you can see that all the elements in the network should cooperate in this process. Then we have two different parameters here, price of service and cost of caching. These are two variables that these players, access ICN, transit ICN, and also content provider, or maybe the users, will compete for that. And they want to get more payoff from this actually conflict situation. Then we can model this problem as a non-cooperative game for pricing and caching, and we can look at this problem as two different cases. The first case is a static case, when we assume that the caching cost is fixed for all the players all the time. The second one is dynamic case, that we assume that caching cost is varying according to the state of the cache. And when the cache is more full, then we need to have and slight increase in the caching cost. This is the system model that we have considered for this problem. We have one transit network, one content provider, and two access ICN A and B, and we have a bunch of users that can switch freely between these two access ICN, and each player has a set of caching and pricing strategies, and all the players want to maximize their own payoff selfishly in a non-competitive game. Access ICN charge price PA to user and also charge price PAS as a storage price to content to transit network C if the transit network needs the access ICN content. Transit ICN also will charge the price PC to the access ICN, and content provider will charge the price POC for the content to users and charge price POS as a storage price to transit network when it's cache the data or the content that transit networks need. And we also we have a user demand function that is linear, and it's linear according to the price PA, PB, and POC, that is the content price. Actually, we borrowed this model from someone else, and we have done our work based on that. These are the parameters for this game. I just want to mention that the CK is the caching cost of ICN K, and alpha KM is the fraction of ICN K demands that comes from cache M. Based on this parameter, we can formulate the utility function for all the players based on the demand, the fraction of stored content, the price, and also the caching cost for each player. For the access ICN and transit ICN, this payoff is the sum of two different terms. The first term is for caching the data. The other term is for forwarding the data. And for the content provider, the payoff will be based on two terms. The first one is the payoff from caching the content, and the second one is the payoff that it obtained from selling the content. Now we go through this static game. This one is a non-competitive game, and the caching costs for all the players are fixed, and the game just played for one time. The assumption that we have here is the content in each request are different or unique. Yes?
So you don't include the transportation cost here? So like
actually,
advantage of caching might be like you get gain from
actually this PA, yes, this PA is the sum of transit price and also the caching price. The sum of these two. Because when this one try to send some content to user, then it will transit it and also cache it. Then this price PA can be represented for both of them.
So then P naught would be different for the directly to the user to the transit method.
Which one? PA?
P0.
You mean POF?
Yeah.
POC?
Yeah.
This one is the price that it will the user will pay for the content, not for the transit or caching. For example, I just want to see a movie. I need to pay some money for the, I don't know, for the company that have made the movie, and some money to someone that it delivered to me. It's different. As I told, the content in each in the game is different in each request. For example, none of the user wouldn't request for a piece of content 2 times. And the optimization problem that we have here is to maximize the utility function for each player based on the setup strategy PJ and alpha J, that is pricing strategies and caching strategies, while the other player choose a strategy S minus J. The result that we got for a network that is consists of 2 access ICN A and B, 1 transit ICN C, and 1 content provider O, at the Nash equilibrium will be the caching variables alpha Km take on value of 0 or 1, because there is a linear relationship between the utility function and also the caching variables. And if we assume that access ICN A and B are not symmetric, it means that the parameter that we use for these 2 access ICN are not the same, then we can have 9 different cases possible that depending on the choice of caching parameters that can be Nash equilibrium. And for the case that A and B are symmetric, then there are only 3 Nash equilibrium possible. And we just go through the results for the symmetric case. These 3 cases are, the first one, we call it the generic case, and it's when the transit ICN caching cost is greater than the access ICN caching cost. In this case, all the content will cache in the access ICN. The second one is C-dominant case. Actually, C is representative for the transit network. And for this case, transit ICN will cache all the demands. And when it happens, when the transit ICN caching cost is less than both access ICN caching cost and content provider caching cost. And the third case, that is O-dominant case, and content provider will cache all the demands. And when it happens, when the transit ICN caching cost is less than the access ICN caching cost, but it's greater than the content provider caching cost. This is the utility table for all these 3 cases. For the degenerate case and C-dominant case, the results are basically the same except for transit ICN. But you can see for the O-dominant case, the result is completely different from the first 2 cases. And the important term here is the difference between CC minus CO, the caching cost for transit network and caching cost for content provider. And this will make so many changes for the result. Now we will go through the dynamic game. That is actually, this problem naturally is a dynamic game. Then we can consider a game that will be repeated over time. And for this game, we have this fact that the cost of caching is varying according to the state of the cache. Each time that our cache is a little bit full, then the caching price will increase. And we have 2 different trends for this one. The first one is linear cost, the other one is exponential cost. I have 2 different parameters here, CK0 that shows me the initial internal caching cost, and zeta that shows me how fast the cost changes with a state of the cache, that is ZK. And we start from the empty cache, and at the end of each round of the game, the caching cost will be updated based on the state of the cache, and the payoff for each player is the average over the rounds. And we note that all the results for a static game will be applicable for the repeated game also. To summarize our discussion, these are some figures that we have from our numerical analysis. This page is for access ICN in linear case. The top left figure shows us the caching cost versus the round. You can see that for sometimes the caching cost is fixed, and after sometimes it starts to increasing. And for example, for the red one, for the red line, that is for access ICN, it is fixed until the round 90 something, and after that it increases linearly. And why is it happening? Because the caching cost for the transit ICN until the round around 90 is less than the caching cost of access ICN. Then access ICN decide to forward all the requests to the transit ICN to get more payoff. And at the top right, you can see the caching strategies for access ICN A. You can see that from round 0 to 90 something, it decides to not cache anything, then the result is just 0. And after that, it starts to cache the content sometimes, and the result is just 1. Bottom left shows the price for access ICN versus the round. I need to say that here that we have not normalized the price, and these numbers doesn't make sense to you, and it's okay because we have not normalized it. And you can see the caching cost for access ICN till around 90 something is still fixed, but after that it's increased linearly. And the payoff is also has a transit time, and after that it start to converge to a stable point. And why this price increase? Because when the caching cost increase, the access ISIN needs to increase its price in order to get more payoff. These are the results for the access ISIN in exponential case. The top left one shows the caching cost versus the round, and it will change exponentially. And the caching parameters or caching strategies also are 0 till around 20 something. After that it starts to be 1 or 0, and the reason is the same as the one that I told for the linear case. Here it starts to cache early because the caching cost for access ICN will grow exponentially. Then it will reach the caching cost of transit ICN, and then sometimes it needs to decide to cache the content itself. And the price that it charged to users also increase exponentially for the same reason as I told before. And this time, the utility for access ICN start to grow up exponentially. And the reason is because we have this O dominant case here, and this one is the utility for this case for the content provider, and you can see that this utility depends on the difference between CC and CO. That is the caching cost for transit ICN and content provider. And because these two parameters are exponential, are changing exponentially, then the difference of these two also change exponentially. And because of that, after some time, the utility will grow up unboundedly. And these are the results for transit ICN for two different cases of linear and exponential. We can see that its price for the first case increased linearly, for the second case increased exponentially. Actually, the price of transit ICN charged to users is following the caching cost of access ICN. And if I go back to the caching cost, you can see that the result for transit ICN price PC actually following the caching cost of access ICN. Here, that is red one. You can see that it starts from 90 something, then increase linearly. And the utility for linear case started decreasing to some point. At some round, it will converge to a stable point. But for the exponential case, it starts to decrease, but after some time, it's again start to increasing. And the reason is again the same as the reason that I told for the access ICN, because of the difference between CC and CO, because both of them grow up exponentially. Then after some time, the utility for transit ICN also increase unboundedly. To summarize our discussion, we have modeled the interaction among access ICN, transit ICN, and content provider in a game, and finding the Nash equilibrium for this game as a solution for a static and dynamic game. And we can say that the result also can be generalized to K-access ICN. And what we have planned to do next is, the first one is to map the prices to dollar per megabyte instead of some nonsense number. And the other one, actually we are not satisfied with the model that we borrowed from another people, and we need to update and improve the demand models. And maybe if we can do this, then we do not need to normalize the result. We can do the normalization in the demand models. And we will need to add also users utility of function to the game, because the results shows that these prices are not fair to the user, because it increase unboundedly sometimes. And the most important thing about this work is we need to add content popularity to this formulation of this game. And we have done a little bit, but the results are not complete. And also, we need to design an online distributed algorithm to implement this game to see in real scenario. And thank you for your attention. Is there any question?